want to thank the organizers for organizing this very amazing seminar series. And personally, I have learned a lot from the previous speakers. So today I'm going to talk about the MCMC sampling complexity for high-dimensional discrete space statistical problems. So although in my title I say that, okay, high-dimensional structural learning and other discrete space problems, but actually in my talk, I will first talk about the general theory, and then I will move on to talk about a more specific problem, which is the structural learning problem. So I will begin my talk by just kind of setting up the background, giving you some examples of discrete space statistical models, which will motivate, say, the general framework I'm going to use. And then I will move on to just show you, say, the general theoretical results we have, and some possible extensions. And when we move on to the structural learning, I will show you how we can apply, say, the general theory to this particular statistical problem. Okay. So first, so my talk is about the discrete space problems. But let me first just say something about the statistical models with continuous parameter spaces. So for Bayesian problems with continuous parameters, if you are willing to assume asymptotic normality, then actually you can develop very general theoretical guarantees for the MCMC sampling, well, specifically for the Metropolis-Hastings algorithms. For example, one pioneering work in this spirit was done by Belloni and Chernozhukov in 2009. So they assumed that, so they used the Bernstein-von Mises theorem and assumed, say, the approximate normality of the target distribution, and then you can use isoparametric inequalities to obtain the sampling complexity of the random walk Metropolis-Hastings algorithm. And then in a recent paper by Tang and Yang, they considered a very similar setup, and then they obtained the complexity for MALA, for Metropolis-adjusted Langevin algorithm. And I just want to say that, so if you are willing to further assume, for example, the target distribution is log concave, or say it satisfies certain functional inequalities, then of course you will be able to apply a lot more existing theoretical results to characterize, say, the complexity of your Metropolis-Hastings algorithm. And also, if we are interested, and also if we look at, say, the complexity results for specific statistical models, for example, Bayesian logistic regression, then again, there exists a very, very big literature on the convergence rate, on the mixing rate of all kinds of MCMC algorithms, especially for Gibbs sampling algorithms. And I think some of the organizers have written a few very nice papers on these topics, but that literature is a little bit too big, so I cannot, list those papers here. And in my talk, we are interested in the discrete space setting. So for this, on discrete spaces, I guess we can say that there's no standard asymptotic regime or standard limiting theorem which can help us, choose this general framework to work with. But still, if we look at, say, these common discrete space statistical problems we encounter in Bayesian statistics, then they do share a lot of characteristics in common. For example, the underlying state space is usually very large, and it grows super polynomially with respect to some complexity parameter. And I just want to say that in this talk, I'm interested in the high-dimensional setting, which means that, well, the problem complexity will go to infinity. Okay. So we care a lot about, say, the growth rates of, for example, of the underlying state space. Although the underlying state space is super polynomially large, but if you look at, say, how people really run, say, the MCMC sampling algorithms on these state spaces, then usually they consider local MCMC algorithms, local Metropolis-Hastings algorithms, by which I mean that in every iteration, the sampler can only move from the current state X to another state which is nearby. Okay, so this search neighborhood is typically very small in the sense that it is only polynomially large with respect to the complexity parameters. And in these settings, a very natural question we can ask is, then do we have, say, a polynomial mixing time of our MCMC sampler? And if, let's say, it is indeed a polynomial, if, let's say, the mixing time indeed scales polynomially, then we say that, okay, the MCMC sample in this case is rapidly mixing. Okay. So now I'm going to just show you some typical examples of discrete space statistical problems to kind of illustrate this idea of the search neighborhood. So the first example, which I guess is the the most common and standard example, is the variable selection problem. So here we are considering, say, how to choose among, say, p candidate predictors to build a linear regression model for explaining some response variable. So the underlying state space is going to be the collection of all possible models. So its cardinality is going to be, say, 2 to the p. But when we really run the MCMC algorithm, a common strategy is to just consider, say, adding or removing a covariate in every iteration. And in this case, so it's kind of trivial to see that the search neighborhood size is only equal to p. Of course, sometimes we also consider swap, but then the neighborhood size is still polynomial in p, so it's just roughly speaking p squared. And another kind of famous example of discrete space problem is community detection, which is also known as stochastic block model. So for this problem, we are interested in learning the community assignments of, say, p individuals. And let's say that we have k communities, and then the underlying state space is all possible assignments of these p individuals. So this is going to just be the product of the set, say 1, 2, 3, blah, blah, until this big K. So of course, this is exponential in p, even if we assume K, is a fixed constant. But then when we think about it, say how we kind of do this, say MCMC algorithm for this problem, then usually in every iteration, we only consider, say, changing the assignment of one individual. For example, here, let's say that we have 2 clusters, the blue cluster, the purple cluster. And now if we change, say, the assignment of this individual, then I get, say, this new assignment, a new community assignment. So in this case, the search neighborhood size is, again, just polynomial in P. Okay. So the next example is going to be kind of more complicated. So we consider decision trees, or we just say the cart model. So for decision trees, let's say that we only have one numerical variable, say maybe we denote it by big Z, and then we can choose, say, p possible locations for splitting, for the splitting rule, in building this decision tree. And then our underlying search space will just be the collection of all the possible decision trees with splits chosen from these p locations. And you can show that it is at least, say, exponential in p. But when we think about how we do MCMC, how we kind of compute the posterior of this Bayesian cart, then usually what people do is that they consider two types of moves. One is called prune, one is called grow. And for this example we have here, let's say this numerical variable z takes values in 0 to 8, and we have 7 possible splitting locations, 1, 2, 3, 4, 5, 6, 7, and then this is our current decision tree. Then if you do the pruning, then you can get, say, these 2 possible decision trees, and if you do the grow, then you can get these 4 possible decision trees. So in this case, again, the search neighborhood is just going to be at most p, so it's going to be polynomial in p. Okay. So the next problem, which will also be the topic of the second part of this talk, is the structured learning problem. So for this problem, we are trying to infer, say, the underlying directed acyclic graph from some observations. And if you have p node variables, then the underlying state space is the collection of all the p node DAGs. And according to a well-known formula due to Robinson, you can show that, okay, the size of this state space is super exponential in P, and actually it is very large. For example, for P equal to 10, this is already a very, an enormous and astronomically large number. Okay. So here I'm just, for example, I'm considering, say, this DAG model. And now if we consider, say, how we do the search on the DAG space, then a common strategy is to consider, say, 3 possible local moves. Say we add an edge, or maybe we remove an edge, or maybe we reverse an edge. And because, say, and because we have p nodes, so the number of all possible edges is only, say, p squared. And then this implies that the search neighborhood size is again only polynomial in p. Okay. And for the structured learning problem, you can perform search on this DAG space, and you can also perform search on another space, which is called the order space. And this is because every DAG is consistent with at least one topological ordering. So you can first consider how to learn this topological ordering from the data. And given the ordering, well, you can run some variable selection algorithm to infer the DAG. And now if, let's say, you do this order learning, then the underlying state space is going to be the collection of all the possible permutations of 1, 2, 3, blah, blah, until p. So this is, again, super exponential in p. And then how we kind of do the MCMC algorithm on this permutation space, one common strategy is to consider, say, adjacent transpositions. Then, of course, in this case, the size of the search neighborhood is going to be p minus 1, so there's polynomial in p. And you can consider other, say, local moves. For example, you can allow, say, all possible transpositions, but then that's, then that gives you, say, the p square size for the search neighborhood, which is, again, polynomial in p. Okay. So these are just some common examples for the discrete space statistical problems. So we see that the underlying search space is very large, super polynomial in P, but the search neighborhood is kind of always polynomial in P. Okay. So this makes the previous question, I mean, on rapid mixing sensible. So we can kind of ask, okay, do we have a useful algorithm which can achieve, say, polynomial mixing time under some conditions? Of course, if we cannot say anything about the posterior distribution, then we won't be able to derive any useful mixing time guarantees because the underlying search space is too large, right? So we have to be able to say something about the behavior of the posterior so that we can derive mixing time guarantees. And this motivates us to look at, say, what are the existing, say, theoretical knowledge we have about these discrete space statistical models. And actually, so there's, again, a vast literature on the posterior consistency and the posterior contraction results for all these discrete space problems I have talked about and many other discrete space problems. Basically, once you impose some appropriate conditions on the underlying, say, on the underlying search space, especially the sparsity, and you also have some assumptions on the prior distributions and how the data is generated, then you will be able to show that the posterior distribution should concentrate around the true model, and you will have some kind of minimax rate in terms of the posterior prediction loss. And here I'm quoting, say, this true model because sometimes you want to define this true model in a slightly, say, tricky way. For example, for variable selection, you may want to define this true model as the collection of all the variables with a significantly large effect size. And then basically here you are just ignoring, many other variables which may have effect on y, but the effects are just too small. As I said, the literature on this topic is just huge. So even if we just consider variable selection, it's impossible to enumerate, say, the literature on the posterior consistency or the contraction rates for variable selection. So here I'm only just showing you, say, one paper by Gao, Vanderwaart, and Harrison Zhou, because in this paper, these authors built a general framework for studying some discrete space problems. So their framework actually covers a lot of problems, some of which were mentioned earlier. And they built some kind of general theoretical guarantees for the behavior of the posterior distribution for these discrete space problems. For example, they obtained the minimax rate for the posterior prediction loss. So I guess the point I want to make here is that although discrete space problems, they are, so each problem is kind of different. So I mean, discrete space problems, they kind of differ from each other, and each problem has its own unique challenges. But apparently, it is possible to say something in general about, the posterior distribution for these discrete space problems. However, for these theoretical results, usually people only consider, say, the theoretical properties of the posterior distribution, and they don't consider, for example, the computation of the posterior distribution. So there's apparently, if we look at this literature, apparently there is a significant statistical computational gap in the sense that if you want to achieve, say, complexity guarantee for your sampling algorithms, or just any kind of guarantee for the algorithm you use for computing the posterior distribution, then apparently you need to impose, say, more assumptions or maybe even stronger assumptions, say, on the model, on the prior, and maybe the true data generating mechanisms. Okay. And the literature on the sampling complexity for these discrete space problems is much smaller than the literature on the general statistical theory. Perhaps it's because the sampling is a little bit more challenging to study. But anyway, in recent years, the literature on the MCMC sampling complexity for these problems was growing very quickly. And here I'm just showing you some of these papers related to the problems I have mentioned earlier. For example, variable selection. This is probably the most widely studied problem, and there are quite a few papers on the complexity of MCMC sampling for variable selection. And there are also papers for community detection for structural learning, and also these decision trees models, say CART and even BART. Okay. BART just means additive trees. So we are considering, say, multiple CART models, so which is of course going to be a lot more complicated than the previous CART example I showed you. But still, there are I mean, there were some recent papers on the sampling complexity for both CART and BART. Okay. So this is the introduction of my talk. And next, I'm going to move on to say some general theoretical results we develop, say, for these discrete space statistical problems. Of course, to derive some general theory, the first thing we want to do is to choose a reasonable, theoretical setup to work with. And motivated by the previous discussion, so I'm going to set up my problem as follows. So first of all, so we are only considering the Metropolis-Hastings algorithms. So I'm using pi to denote my target probability distribution, so which is my posterior distribution of some Bayesian statistical model with a discrete parameter space, say this calligraphic X. And for every state little x, I'm using this nx to denote, say, the set of states that the Metropolis-Hastings sampler can propose at x. So the sampler can only move from x to some state, say y, in this neighborhood set nx. Okay. And I'm using x star to denote the mode of pi, and I'm assuming that this x star is unique. So you can think of it as the true model, or maybe you call it the true parameter value. Okay. And as we have discussed previously, under some conditions, we would expect that, okay, the posterior distribution will probably concentrate on this x star. Okay. And to characterize the mixing time bounds, I need to introduce two parameters. So they will be essential to our theoretical development. So the first parameter, this big M, denotes the maximum size of these neighborhood sets, say nx. So this M is just an, well, more general, you can just say that this M is an upper bound on the size of the neighborhood set nx. And another parameter, which I call R, roughly speaking, can be interpreted as a measure of how unimodal your posterior distribution is. Okay. So this R can be defined in such a way. So for any x that is not equal to this x star, for any x that is not the mode of the posterior, there is some neighboring state, say y, such that pi y divided by pi x is greater than or equal to, say, this parameter r. Okay. So basically, what I'm saying is that, okay, so as long as I'm not at, say, the global mode, then I will be able to pick, say, some neighboring state y, which is kind of, sufficiently good. And in our theory, so we will consider the following conditions, say big R greater than big M or big R greater than big M squared. So this is basically the only assumption we need for our theoretical development. And if we look at this definition again, so basically what I'm saying is that, okay, so if I'm not at the current global mode, if I'm not at, say, the true model, then I will be able to pick a neighboring model which is much better than the current model. So much better just means that the posterior probability is much larger. Okay. And this is why I say that we can view this condition as a local consistency property of the underlying statistical model. So it is, of course, stronger than the global consistency. By global consistency, I mean that, for example, we can say the posterior mass of the true model converges to 1. So that will be a global statement. But here we want to require a little bit more. So we want to have some kind of local consistency properties so that I can categorize, say, how the sampler behaves, say, locally at every possible state, little x. Okay. And because this is a little bit stronger than a global consistency, so if you want to prove, say, these conditions using the high-dimensional statistical tools, then you will need to require a little bit stronger assumptions than those needed for posterior consistency or posterior contraction. Okay. But anyway, so this has already been done in the literature for quite a few problems. And some of the literature have already been mentioned previously. For example, for variable selection, these assumptions are actually well studied. Okay. And from the perspective of, say, proving, say, this condition using the high-dimensional statistical theory, there's actually very little difference between assuming, say, R greater than 1 or R greater than M or R greater than M squared, because all you need is just to modify some universal constants in the proof of these conditions. For example, for most of these problems, you will need to require a condition, which is called the beta mean condition, which basically says what's going to be the say the minimum size of some non-zero effect, or you can say what's the minimum size of the signals. So you want to make sure the signal is large enough to be detectable, and then if you tune the universal constants in these beta mean conditions, then you will be able to get, say, for example, strengthen, say, R greater than 1 to R greater than M squared. So from the statistical theoretical perspective, these two conditions are just, say, equally strong. Okay. Of course, I want to say that these conditions these conditions are still often, kind of too restrictive. But I would say that at least this local consistency setting is a very natural and a reasonable setting to begin with when we consider, what's the complexity of the MCMC sampling. So once we are able to say something in this regime, then we can consider, say, how to extend our results to more general scenarios. Okay. And actually, this condition is not, say, really that strong. And here I call it weak local consistency because we are not making any other assumptions. In particular, we are not making assumption on, say, which neighboring states or how many neighboring states satisfy this condition, say, pi y over pi x greater than, say, big R. For example, this is the previous variable selection problem. Let's say if my current model is 1, 2, and let's say maybe the true model is 2 and 3, then this better neighboring model could be this model, could be this model, or it could be this 1, 2, 3 model. So we are not making any assumption on which of them is the better model or how many of them are the better models. All I'm assuming is that there's, as long as I'm not at the true model, then there's one better, say, neighboring model. Okay. So this is the theoretical assumption we make. And for the Metropolis-Hastings algorithms, so I consider, say, two classes of Metropolis-Hastings algorithms. The first class is just a random walk. So we are going to just propose one state in this neighborhood set randomly with equal probability. And the second class is the informed Metropolis-Hastings algorithm. So here I'm considering, say, this construction. So I will propose a neighboring state with probability proportional to, say, this function, h pi x prime over pi x. And then this function h is just, say, equal to, say, this ratio, but we truncate it using the lower bound, say, little l, and we truncate it at an upper bound, at an upper threshold, say, this big L. Okay. So this is going to be my informed proposal weight for the neighboring states. Okay. So you can say that in most cases, it is just equal to, say, this posterior ratio, say pi x prime over pi x. But if it is too large, we truncate it. If it is too small, we also truncate it. And this truncation is actually quite essential to deriving theoretical guarantees. Okay. And this informed proposals has gained a lot of attraction in recent years, and it has been used in many MCMC methods and even non-MCMC methods. The first time you see these informed Metropolis-Hastings algorithm, you may think that they may behave, they may converge much faster than random walk Metropolis-Hastings. So if you think of a random walk Metropolis-Hastings as say a turtle, then you may imagine that, okay, maybe the informed Metropolis-Hastings can behave like a rocket. Well, this is not really the case. So the reason is that when we think about how we implement these informed proposals, then in every iteration, I need to evaluate, say, the posterior probabilities of all the neighboring states so that I can, say, implement this informed proposal. And then this evaluation, of course, takes a lot of time. So every iteration of the informed Metropolis-Hastings is going to be a lot more time consuming than the random walk Metropolis-Hastings. Okay. And actually, there are some cases where if you don't devise this informed proposal scheme carefully, you can even end up with some algorithm that behaves much worse than the random walk Metropolis-Hastings. Okay. But I guess these days, because of the increasing availability of parallel computing, so I do think informed Metropolis-Hastings algorithm will be more and more useful because you can kind of parallelize, say, this posterior evaluation. And then if you choose the informed proposal carefully, you will be able to beat random walk Metropolis-Hastings by a large margin. So here is just a summary of the mixing time bounds we obtained in our paper. So I consider random walk Metropolis-Hastings, and for random walk Metropolis-Hastings, I will impose the assumption R greater than M. And for the informed Metropolis-Hastings, I will impose the assumption that R is greater than M squared. And for the clipping parameters, little l and big L in my informed proposal, I assume little l is equal to big M, and I assume big L is between, say, M squared and big R. And under these conditions, we can obtain the following mixing time bounds. Okay. And again, I just want to say that we are not considering the per iteration computational cost. So for informed MH, its actual complexity is going to be much larger than this mixing time estimate here. Okay. So this is a summary of our theoretical results. And next, I'm going to kind of discuss, these three entries. So you see that here in this table, I'm considering two different proof techniques. One is the pass method, one is the drift condition. So I think both methods have been widely used in the MCMC literature, but usually drift condition, drift and minorization condition is more widely used for continuous space problems. But for this problem, we were able to prove, say, the mixing time bounds using both pass method and the drift condition. And personally, I also think that it's quite interesting to compare the behavior, the results we obtain using these two different methods. I think in general, we cannot really say that much about, say, which method is more advantageous, but at least under this setup, the mixing time bound we obtain using the drift condition is actually a little bit better than the mixing time bound we obtain using the pass method. So you may wonder, what is pass method, what is drift condition? So I'm going to briefly talk about this. Okay. So let's look at, say, this entry first. So this is the complexity for random walk Metropolis-Hastings. This is the easiest one. So the proof is quite standard. So you just consider the classical canonical path method, which basically means that you identify a likely path from any state x to x star. And once you can identify this path, now you just kind of analyze, say, the congestion at every edge. So by congestion, I just mean that you try to quantify what's the traffic load of every edge, and you also quantify what's the capacity of every edge. And then you consider, say, what's the ratio of traffic load against the capacity, and you can quantify the congestion. And this congestion parameter yields a bound on the spectral gap, and the spectral gap yields a bound on the mixing time. Okay. But I just want to say that the argument we used was a slightly improved version, in the sense that we used a slightly more general path method, so that our bound here does not involve, say, the length of these paths. Okay. So if you just follow the standard canonical path method, then in your final mixing time bound, there will be an extra term describing what's the maximum length of these paths. But actually, this factor can be dropped by just slightly improving this argument. But for informed Metropolis-Hastings algorithm, the proofs will be kind of a lot more complicated. So if we first consider the path method, then the canonical path method is not going to work. And the main reason is just that you are only identifying, say, one likely path from every x to x star. But for the informed MH, so if you look at this mixing time bound, we want to show that, okay, this mixing time bound does not explicitly depend on this neighborhood size, big M. So if I want to, get rid of this factor M, then I have to identify, say, sufficiently many likely paths from every state x to x star. So I have to consider, say, all these good paths so that I can obtain, say, a tight bound on the mixing time. And after we identify these paths, you also need to kind of figure out how you assign different weights to these paths so that you will be able to bound, say, some kind of congestion ratio. And this technique is sometimes called the multicommodity flow. And I think this is also kind of a very well-known technique in the Markov theory on discrete spaces. Okay. And finally, so in this entry, so we were still studying the informed Metropolis-Hastings algorithm, but we proved the mixing time bound using another technique, that is the drift condition. Okay. So the drift condition we are using here is one, well, I mean, for both of you who work on the drift and the minorization conditions, you know that there are just many versions of the drift and the minorization conditions. And although we are considering a discrete space here, you can also kind of just adapt those arguments and apply those results to the discrete space. But here we chose to use this particular version of the drift condition result from the PhD thesis of Jerrison, because the bound is quite clean, and I think it's also kind of better than some other approaches. Okay. And to use, say, this single element drift condition, so the most important step is just to pick a suitable drift function, say Vx, and then you try to verify this inequality, and you try to quantify what is this coefficient, say little alpha here. And this is our construction of the drift function Vx. This is probably one of the most interesting results in this paper. So we construct our drift function Vx in this way. So it is, say, pi x raised to 1 over log pi min, where pi min is just the minimum posterior probabilities on the entire state space. So why do we choose this? I don't have, say, a very good, say, intuitive explanation. All I can say is that we actually tried many other drift functions, and none of them were able to, say, give us, say, the mixing time bounds that we were happy with. But this drift function just somehow makes the argument works. And once we have picked, say, this drift function, the rest of the proof will be kind of more or less straightforward. You just say directly, you just try to verify this inequality by doing some algebra. And I think I also want to say that if you look at, say, the literature on the general theory of the MCMC complexity on continuous spaces, people have also used, say, the drift and the minorization condition. And in those cases, the drift function usually takes the form, say, 1 over square root of pi x. So it is kind of similar to what we have here, but we see that this exponent is different. Okay. And then this is the final bound we obtained. So we have kind of, you'll see that this is a little bit better than this bound we obtained using the PASS method. Okay. And I think I can briefly talk about, say, how we can extend, say, this theory to more general settings. So first, I want to kind of consider, say, this generalization to the so-called unrestricted search space. So if we look at, say, the previous, previously I mentioned that there's a huge literature on the, the posterior properties of these discrete space problems. And when you look at this literature, a very important assumption is on the model sparsity. Okay. So you have to make some assumptions on the sparsity of your underlying model, so that you will be able to achieve, for example, posterior contraction, or maybe prove, say, the sampling complexity. And theoretically, this is because we are considering a high-dimensional regime, and if you don't impose any kind of sparsity constraints, then you won't be able to say anything about the behavior of the posterior distribution on non-sparse models. So the behavior of the posterior distribution on non-sparse models can just be very weird. We cannot really say anything about it. But from a practical perspective, actually you may wonder, do we really have to work with the restricted space in our MCMC sampling complexity? So let's say that here we have a blue region, which is my restricted search space satisfying the sparsity constraints. And then I have a gray region, which is the unrestricted space. Then if I initialize, say, my sampler here at this x0, then probably my sampler will behave like this. And then after some time, it will reach, this x star. Okay. And the point is that probably during say, my run of the MCMC algorithm, my sampler will never leave, say, this restricted space. For example, if we think about the variable selection, so you can impose a sparsity constraint, which means that you only consider models with at most, say, maybe 100 variables. Okay. But as you run your MCMC algorithms, probably all the models you sample, I mean, they are relatively small. Say they can have, say, maybe 10 variables, 20 variables, but they will never reach, say, 100 variables. So this makes one wonder, say, why the behavior of the posterior, say, outside of this restricted space matters for the MCMC complexity, or how can we kind of overcome this? So there's a recent paper by Eva Achadi, which provides a very nice solution to this problem. So he proposed to use the restricted spectral gap to study the Markov chain mixing times, and he studied the variable selection problem, and he showed that how you can use the restricted spectral gap to extend the rapid mixing result on the restricted space to the unrestricted search space. Okay. So basically, you need, say, these two conditions. Okay. So first of all, you want to show that your probability mass, your posterior probability mass, concentrates on the restricted space. Okay. So if you look at those non-sparse models, their posterior probabilities are negligible. Second, if you think about how you run this MCMC algorithm, you want to make sure that you are using a warm start. So for example, you are initializing your sampler inside of this restricted search space. Then under these two conditions, if you consider random walk Metropolis-Hastings, you will be able to have a rapid mixing guarantee on the entire, say, unrestricted space. Okay. But for informed Metropolis-Hastings, we found that you just need to impose, say, one more condition, and that is at the boundary of this restricted search space, you want to require that the proposal probability of the states that are not in the restricted space is not too large. So this is just to guarantee that, you are not, say, your sampler is not going to kind of, it's unlikely to leave, say, your restricted search space. And with this extra assumption, then basically, so you can just extend all the previous mixing bounds to the unrestricted search space. So this is just one possible generalization of the theoretical result. Okay. And here is just a simulation we did on the community detection problem. So for this, recall that we are interested for this problem, we are interested in the community assignment of, say, P individuals And here I'm considering, say, 1,000 individuals, and I only consider 2 possible communities. And then I consider 2 possible initialization. For the good initialization, we let 1/3 of the assignments be incorrect. And for the bad initialization, we let 1/2 of the assignments be incorrect. And when we look at, say, this trajectory of the log posterior of our MCMC runs, so these blue lines represent the runs with good initialization. We see that they actually quickly reach, say, the true model. The log posterior probability increased very fast, and then after some iterations, we were able to find the true model, which is indicated by the red line. But now, if you consider the bad initialization, which are represented by these gray lines, then very often, I mean, say your sampler just kind of gets stuck, and it cannot, say, find the true model even after a very big number of iterations. And if you compare the behavior of the random walk Metropolis-Hastings with informed Metropolis-Hastings, so the left is for the random walk, the right is for the informed. So you will be able to see that actually the informed Metropolis-Hastings algorithm is kind of even more sensitive to the initialization. This is, of course, not too surprising because informed algorithms, they kind of, put a lot of, proposal probabilities on those seemingly good, say, neighboring states. And if your initialization is bad, if you initialize your informed sampler, say, in a bad region, then it's very likely, it's more likely for the informed Metropolis-Hastings to get trapped there. And indeed, in our simulation, we see that this contrast between the two algorithms is quite obvious. Okay, so this is the general theory. So we have, I think I have maybe 5 to 10 minutes left. So I will briefly comment on, say, how we apply this general theory to the Bayesian structural learning problems. So this is, the structural learning is kind of a very challenging discrete space statistical problem. So we want to learn, say, the so-called the DAG models. Okay. And each DAG model encodes the conditional independence relations in the joint distribution of P node variables, node variables, say x1, x2, blah, blah, until xp. And the structural learning just means that we want to recover this DAG model from n observations of the random vector, x1, x2, blah, 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 until this big xp. Okay. So intuitively, if I want to apply my previous general theory to the structural learning problem, then all I need is just to, construct a random Metropolis-Hastings algorithm, and then I check, okay, if that, say, R greater than M condition can be satisfied. But actually, this turned out to be very, very difficult to prove for the structural learning problem in the high-dimensional setting. So you really need to spend a lot of time figuring out, say, what is the right search space to work with, and what is the search neighborhood to use. If you don't choose them properly, then actually you won't be able to have, say, any kind of, say, statistical guarantees on the local behavior of the posterior distribution, and of course, your sampler may mix very slowly. So why for this structural learning problem, it is finding the search space, finding the search neighborhood is so complicated. So there are a couple of reasons. And here I'm only going to kind of just briefly mention one major reason, which is the existence of the so-called Markov equivalent DAGs. So for those of you who are familiar with DAGs and the causal inference, so of course you know this. So two different DAGs may encode exactly the same set of CI relations, in which case we say they are Markov equivalent. For example, if we consider, say, these 4 DAGs here, then the 3 DAGs in the green box, they are all Markov equivalent. And this V structure is different from these 3 DAGs here. Okay. And why the Markov equivalence class is annoying? Because if you only have observational data and you don't have prior knowledge, the Markov equivalent Gaussian DAGs, they are not distinguishable. So if you construct your posterior distribution properly, then the posterior probabilities for Markov equivalent DAGs will be exactly the same. And what is even worse is that the size of these Markov equivalence class can be really, really large. For example, here, I'm just considering a very sparse models, so which has, say, P over 2 many edges. But if you consider how many DAGs that are Markov equivalent to this DAG, then there are exponentially many DAGs that are equivalent to this one. Okay. So the size of a Markov equivalence class can easily be exponential in P, even if you assume the node degree is sparse in your DAG model. Okay. And then now, if you think about what would happen if you run your MCMC sampler on a DAG space, then the good news is that you can use edge reversals to move between any two Markov equivalent DAGs. However, it is still very unclear if your sampler can leave a Markov equivalence class in polynomial time, even if you impose some sparsity constraint on the node degree. Okay. So some Markov equivalence classes can just be too big, and then your sampler may just get trapped in this Markov equivalent class, moving between all DAGs that are actually Markov equivalent. And if this takes super polynomial time, then your sampler will not have polynomial mixing time guarantee. So this is one major reason why this problem is difficult. And then intuitively, so one solution I guess we may come up with immediately is that can we introduce, say, a type of proposal that allows us, say, to jump from one DAG to any other DAG in the same Markov equivalent class, so that I can kind of immediately achieve, say, rapid mixing within every Markov equivalence class. So this is actually very difficult in practice because counting or enumerating a Markov equivalent class is highly time consuming. And then the best algorithm that I know actually has this complexity where D is the degree of your the node degree of your DAG. And if you let D go to infinity, then this complexity is going to be super polynomial in P. So you don't have a polynomial algorithm for counting or enumerating a Markov equivalence class. Okay. So what is the solution we propose? So our solution is that, okay, we just directly construct the Metropolis-Hastings algorithm on a space of sparse Markov equivalence classes instead of constructing the search algorithms on the space of all the sparse directed acyclic graphs. Okay. So limited by time, I'm going to omit, say, a lot of details here, and then let me just kind of show you the main theoretical result and the theoretical insights we obtain from our analysis. Okay. So eventually we decided to work with this search space, which we call the sparse Markov equivalence class space. So we say a DAG G is sparse if I can bound both its in degree and its out degree. And then we define our search space to be the collection of all the Markov equivalence classes that contain at least one sparse member DAG. And then for the searched neighborhood, it is defined in the following way. So we allow the sampler to move from one sparse MEC class to another sparse MEC class, as long as for the first MEC class, there is a DAG G, and for the second MEC class, there is a DAG G prime, such that G prime can be obtained from G by adding, deleting, or swapping an edge. Okay. So this is how we construct the search neighborhood. And this construction is actually very similar to a very famous algorithm in the structured learning literature, which is called a GES, greedy equivalence search, which was proposed by Chickering in this seminal paper. And this algorithm has low dimensional consistency guarantee. And in our setting, what we want to do is to kind of consider what will happen in high dimensional setting. So what are the assumptions we need for example, for D in, D out? What are the assumptions we need for the true model so that in the high dimensional regime, we will also have some kind of guarantees for the MCMC sampling. Okay. And we found that the key condition we need on the sparsity parameters is that we want to require the in-degree constraint to have this order, say the square root of log p. So it can go to infinity, but it cannot grow to infinity very fast. It can, well, actually, it can only grow to infinity at a very, very slow rate. And for the outer degree, it can take this order, say the log p. And for the true data generating DAG, so its node degree also needs to satisfy, say, this order, say the square root of log p. And then under these conditions, we will be able to kind of verify the previous, say, the so-called weak local consistency condition I was proposing in the general theoretical framework. And then we can derive, say, the mixing, and then we can derive the mixing time bounds for both the random walk Metropolis-Hastings algorithm and for the informed Metropolis-Hastings algorithm. Basically, all you need to do is just to kind of plug in those bounds, which involve, say, the priming, and then you do an explicit calculation for figuring out, so what's the order of the minimum posterior probability, and then you obtain, say, your mixing time bounds. Okay. And we see that for the informed Metropolis-Hastings algorithm, the mixing time bounds is much smaller than the random walk. Okay. But of course, the implementation of the informed will be a lot more complicated. So this is almost all of my talk. I just want to conclude my talk with a couple of remarks. So first, I want to say that average discrete space statistical model has its own unique challenges. But in general, some theoretical guarantees can be developed. Okay. Second, I want to say that these mixing time analysis is actually very useful from both theoretical and practical perspectives, because once you conduct the mixing time analysis, it will kind of motivate you to think about, say, what is going to be the appropriate search space I want to work with. And for many discrete space problems, this is actually not that obvious. For variable selection, this is kind of trivial, but for problems like structured learning, we see that this is not really a simple question. And then you also need to think about how you build the neighborhood. Okay? How you build the neighborhood so that locally you will have some kind of consistency guarantees for your posterior distribution. And also, if you think about your informed Metropolis-Hastings scheme, then these mixed time analysis also tell you that how you should choose, how you should devise this informed proposal so that in theory it can behave well. Okay. And I also want to say that our theoretical results, of course, can be extended to more complicated MCMC schemes. For example, you can consider multiple trial Metropolis algorithm. The proof will be largely similar, but you need to impose a little bit stronger conditions and just do a little bit more algebra to kind of deal with the acceptance probability, which is which takes a very complicated form in the multiple trial Metropolis. And then next, extensions of our theory. So I have mentioned one possible extension using the restricted spectral gap to kind of extend the theory from restricted search space to unrestricted search space. But actually, there are many other possible, directions to generalize our theory. For example, in the structural learning problem, we see that if I do the search on a DAG space, then I need to deal with Markov equivalence class. I need to deal with the fact that, okay, in my search, I probably need to traverse a very big Markov equivalence class, and all the models within this equivalence class, they have the same posterior probabilities. So we want, so in this case, the posterior is not going to satisfy, say, that R greater than M condition in our theory, but I think it is possible to kind of generalize the theoretical setup to handle these cases. But eventually, for the structured learning on the DAG space, I think proving the rapid mixing guarantee is still an open problem. So what would be, say, the assumptions you need for achieve rapid mixing on a DAG space? I think this is quite a difficult problem, and it is largely unsolved. Actually, in the first version of our paper, we proved, say, some result on the structured learning on the DAG space, but the conditions were too restrictive, so we removed that result at the end. So this is all my talk. I guess I can stop here. So most of the materials are based on the joint works with my previous PhD student, Woody, who is currently an assistant professor at UT Dallas. Thank you very much for your attention.
Okay, thank you so